let's learn about another type of force and another type of potential energy. That is the spring force. Now, in physics, studying springs is actually super useful and a pretty broad topic. Why do we study springs? It's not because springs themselves are maybe that interesting, although springs can be useful. You have springs in your car for shock absorption. Springs appear in other types of mechanical devices. But the real reason why springs are so interesting in physics is because they are mathematically identical to all sorts of other applications. So if you can understand the math of spring force and spring potential energy, you can also understand the math for other applications, such as the elastic properties of materials, how materials get compressed and change their shape in response to forces. Chemical bonds can act like springs. In fact, almost every force in nature that acts as an attractive or restoring force behaves just like a spring under certain conditions. So all these things that seem kind of unrelated to springs themselves, in fact, are mathematically identical. So let's look at the math of what a spring force is. It's pretty simple. Let me draw a little sketch of a spring. I'll draw a wall and the floor, and we'll put a spring here. So the spring is going horizontally, and right now it's at its relaxed position. If you've ever played with a spring before, you know it has a length that it likes to be when you're not stretching it or compressing it. And so we'll say that the end of that spring here is at position 0. Now, if you compress that spring, squish it, that spring pushes back. So if you apply a displacement, delta x, it's pointing to the left, the spring is going to push back with a force to the right. So this is known as a restoring force because the spring is trying to restore itself to its equilibrium length. Similarly, if you stretch the spring out, if you do a displacement this way, the spring is now stretched too far, it wants to restore to its original position. The spring is going to apply a force to the left. So springs are always trying to get back to their equilibrium length. And the magnitude of this force is proportional to the displacement. And this proportionality factor is known as the spring constant or the force constant. It tells you how strong the spring is. And it has units of newtons per meter, force per length, dimensions of force per length. So that's the magnitude of the spring force. It's proportional to how far you stretch or compress the spring. There's the constant of proportionality. And the direction, we can see from these sketches, the direction of the force opposes the direction of the displacement. So we can summarize that behavior just by putting a minus sign. If you stretch the spring to the right, the spring force tries to pull to the left, hence the minus sign. If you compress the spring to the left, the spring force tries to push you back to the right. Now, spring forces are conservative forces. When you stretch or compress a spring, you do work on the spring. You can recover that work later. The spring will return to its equilibrium position, and if the spring is pushing or pulling on something, it gives that stored potential energy to the object in the form of kinetic energy. So spring forces are conservative, just like gravity forces are. That means we can have a potential energy. All conservative forces have a potential energy function. So the potential energy function for springs looks like this: 1/2 K times delta X squared. It looks kind of like the formula for kinetic energy, 1/2 mv squared, but this is 1/2 K times that displacement squared. And notice that because the displacement is squared, it doesn't matter whether delta X is positive or negative. Stretching or compressing the spring either way will give you positive potential energy. In fact, you can only ever have positive potential energy for springs. It can never be negative. That's a little bit different from gravity, because you can have negative gravitational potential energy if you define the potential energy with respect to some 0 point and you go below that 0 point. But you can't have negative spring potential energy, just from this definition. So let's see a little example of how you could use this. I'll take this picture again of a horizontal spring, but this time we'll put a mass next to it and have the spring push on the mass. Okay, so here's the setup. Initially, we take our spring and put a mass next to it, compress that spring. So it's spring loaded. Now you let go, the spring pushes, the mass slides off to the right. So let's figure out how fast this mass is moving once the spring has pushed it. So let me draw a sketch of the final situation. So in this final situation, the spring has returned to its equilibrium length. It has pushed this mass, and that mass goes sliding off to the right. I didn't mean for the mass to change its shape. So what is the speed of this mass after all this happens? Now again, this is the type of question that you could answer using Newton's second law. This would be complicated using Newton's second law because this spring force depends on position. It depends on how far you've stretched or compressed the spring. And so if you were to try to solve your Newton's second law equation for acceleration, it would be a function of time. You'd have to do calculus to solve it, differential equations. That would be somewhat challenging, beyond the scope of physics 6 for sure. You need to know some more math to do that. But fortunately, we can analyze this problem using conservation of energy with very little effort. It's super easy using conservation of energy. So let's do this. Conservation of energy. And we write down our usual conservation of energy equation. Initial potential plus initial kinetic equals final potential and final kinetic energies. We're ignoring friction, so there's no work done by non-conservative forces. And because this motion is happening horizontally, we don't need to worry about gravitational potential energy, because it's the same for all these objects the whole time. They're not changing their height. Gravitational potential energy depends on height. So the spring and the mass aren't changing their height. Let's not bother with gravitational potential energy. The only potential energy we care about this time is from the spring. So we've got our initial spring potential energy. That's 1/2 K times delta X initial squared. Initial kinetic energy, well, at the beginning, we're just holding everything in place. Nothing is moving. There's 0 kinetic energy at the beginning. And now, final potential energy. Well, in this final picture, oops, I gotta label it final. In that final picture, the spring has returned to its equilibrium length. It's returned to 0 position. So if delta X is 0, there's no spring potential energy. That term is just 0. Right? If delta X is 0, 1/2 K delta X squared is also 0. And the block is moving, so there is some final kinetic energy. And we can find our final speed in not too much more math. Those 1/2s cancel out. And V final is K over M delta X initial squared. Everything is square rooted. Or if you wanted to, you could write it as delta X initial times root K over M. I'll do a homework example in